Hi everyone, welcome to today's ARCHER2 webinar. Today we have Dr. Alessio Castorrini, who is giving us a talk on wind turbine aerodynamics. If you have any questions during the webinar, you can feel free either to put them in the chat or to use the raise hand button at the bottom of your screen. There will also be a time at the end for further questions. So yeah, without further ado, I'll hand it over to Alessio. Thank you very much.
Thank you, and everybody to come to this session. So now, just give me 1 second. I will share my slides. Okay. So this session is about presentation of the activity and some of the results that I got for this HPC Europa 3 project, and I wish to thank the collaboration with my host in Lancaster University, Professor Campobasso, and with a researcher of the group of the National Research Council, Sabrina Gentile, which helps in some of the simulation data that you will see later is going to be used for these results. So what is about first, yeah, as was mentioned, I'm a researcher at the University of Basilicata, which is a university in the south of Italy. I was trained at the Sapienza University of Rome, and now I am also visiting researcher at Lancaster University. So for giving you an overview, a fast overview of the project and aims, let's say that this project was having two main issues that were being addressed during this, let's say, simulation work. And the first is correlated to the study of the wakes and the wind turbine aerodynamics in the wind farm. The background of the problem that is going to be addressed here is coming from the so-called wake effect that sometimes, or maybe often, it's a source of losses for turbines that are behind a row of turbines that is interested by the wind inflow and is releasing a wake, as you can see from this old but very famous picture of an offshore wind farm in the Sea of Denmark. And you can see that in this situation, the turbines that are downstreams respect to the front line sees a flow that is very disturbed by the wake of the front turbines. So one solution that the technology is trying to adopt is to control and to deflect a bit the wakes by orienting the front turbines with a so-called yaw angle, so misaligning the rotor, and in this way using the effect of thrust of the rotor to deflect the wake and free, hopefully, a little part of the rotor behind and saving some energy. In order to verify this kind of solutions and maybe to optimize the design of the layouts of the wind farm, numerical simulation is a very important instrument. However, the accuracy and the affordability of the simulations that you can have with the normal instruments that are on the use for this kind of computation needs to be always verified. And an aim of this project is to make a very high fidelity simulation of a wind turbine rotor to see if a low order kind of model that is used to compute an entire wind farm, so many turbines and many wakes, is able to catch the main features of the aerodynamics of the turbine and of the wake flow. A second point that still is important to assure to have a reliable solution in the numerical simulation of the wind turbines is to give the numerical simulation realistic inflow at the rotor. Now, this inflow condition of the wind, there are many models that can be used to generate them or to predict them. But basically, when you rely on theoretical or classical CFD modeling, these standard models does not seize effects that are connected with the entire atmospheric boundary layer dynamics and also the cycles of the thermal stratification that change a lot, as you can see from this picture, the shape that vertical wind that interests the height of the rotors, because now the last turbines can arrive to elevation of 300 meters from the ground, so they covers much part of the atmospheric boundary layer, and the classical assumption of a neutrally stratified wind flow is not anymore so accurate, because it will not consider thermal convection or thermal stratification. We know that this kind of things can be very well simulated by mesoscale models that are used for the numerical weather prediction. However, these models have a lower resolution in terms of space, and this resolution is often not sufficient to catch surface effects, and in the case of offshore, that is interesting us in this case. For example, it will not be so accurate in case of you want to maybe simulate the effect of the waves on the wind shear, or to have a more maybe detailed wind shear description in the first meters from the ground. So the second part will be an example of how to use CFD coupled with numerical weather prediction and with a particular method to try to include also wave motion in the simulation to check the effect of all these features in the final wind inflow that we can give to the wind turbine simulation. So let's start from the first, sorry, here I think there is a little problem with the conversion of the PDF, but however, in this case, let's start with the first part of the problem, and we see that there are different solutions in the modeling that one can use, and in particular, what we are going to check, what we are going to use in this work is as a low-order model, the so-called actuator line model for the wind turbine, and this will be verified using an HPC simulation of a rotor resolved geometry. Of course, rotor resolved geometry, it means that we create a model, an accurate model of all the geometry, and we don't use a simplification of the turbine in the simulation. So that's why we can use that as a reference to check and to verify the accuracy of the low order model. And about the computational fluid dynamic model, we will see that it's possible to use different kind of modeling based on, for example, Reynolds average and Navier-Stokes equations, or large eddy simulation, which are much more expensive from computational cost, or an hybrid technique to try to get a better resolution of the wakes. some few words about the low-order model that we are going to implement for who is not, of course, an expert in the field. The actuator line model aims to model the wind turbine not with its exact geometry, but substituting it in with a logical discretization in blade elements, and at each blade element the model takes the relative flow to the blade element from the CFD grid, that is a background grid that you can see in the scheme here, and passing this relative wind vector to the airfoil model. It's possible to extract from a table of aerodynamic coefficients the force that is expected to be in the at the element, and this force is then later applied to the CFD simulation in form of a source volume force. This way, it's the flow field sees the presence of the turbine as a source element, and the turbine can be studied in terms of loads and at the elements, and then of course at the rotor by making the integration at each time step of the simulation. So how we implement this in the project? We took a reference model of turbine, which is from this very famous project, the Mexico rotor, to which the references you can find here is a little rotor, but it's provided with experiment a very large database of measurements. So it's a very good starting point to check the accuracy and the validity of the numerical model for the full rotor, that then will be used to verify also the lower order model. In this rotor will be tested, has been tested in 7 test cases. The first 3 to check the validity of the numerical model, which are 3 tests with different wind velocity, from a low velocity to a high velocity. The rotor is rotating always at the same velocity, so that means that the non-dimensional tip speed ratio is different in the 3 situations, and in this case we can test it with these velocities and an axial wind inflow, and also we can check for the case that is more interesting to us, which is with misaligned wind, and measurements are available for 30 degrees, which we make a comparison with the experiment. But also we had a final case with the more tailored analysis of the wake in a typical configuration for wake control with 20 degrees of misalignment. So how we set up the CFD and the numerical solver for this case. Basically, the CFD is based on the 3-dimensional steady and uncompressible Navier-Stokes equation. Turbulence modeling that we are going to apply for studying the turbulence are the Reynolds average Navier-Stokes with the K omega shear stress transport turbulence model, which is an eddy viscosity model, and a hybrid, so more accurate technique that use and couple LES, so large eddy simulation, with the same RANS model used before. The wind turbine will be modeled, as I said, as a full rotor and actuator line model. About the tools that are used for the simulation. We use OpenFOAM as the CFD solving and the CFD solving library, which is already present in ARCHER2. ARCHER2 is the machine where almost all the computations have been done. This library is based on the finite volume technique for the discretization, and it adopts the simple algorithm for steady solution and simple algorithm for unsteady solutions. The parallel computing technique is domain decomposition based on the MPI, and the mesh decomposition for these cases is done using the METIS algorithm. In the case of unsteady simulations, which are the simulations with the misaligned wind, as we will see, a dynamic mesh approach is used to rotate the domain and the rotor, and with respect to the main flow. The generation of the mesh is done by an automatic tool, which is CFmesh. These are all open source codes that can be seized, and you can find documentation at the websites that are shared here. So how we set up the computational domain for this case? We are interested just in the aerodynamics of the rotor and not of the wake. Therefore, we don't need to model the ground. We don't need to model the tower that hold the hub and the turbine. And this will simplify the generation of the mesh. And the domain is simply, as you can see, a cylindrical domain with the dimensions that are enough to guarantee that the effect of the boundary are not affecting the solution of the rotor. So around 10 diameters in any direction far from the rotor are the boundaries. And to the inflow boundaries, we set up the velocity, the free stream velocity and turbulence, as well as in the lateral boundaries, while a Neumann's gradient condition can be used for the outflow. I'm speaking about both the cases with resolved geometry and actuator line, but more in detail, the mesh around the blades in the geometry resolved case can be see some features here in a cut of the mesh. You see the blade, the mesh is refined with the few layers of refinement, catching all the geometry automatically using the curvature, and also there is the we add the boundary layer refinement to better resolve the boundary layer at the wall, and some more levels of refinement around the blades to have resolution of the flow in all parts of the field near to the blade. This makes the mesh to have few millions, we will see how much later, elements. For the case of actuator line, the case is simple, simpler because the rotor geometry that, for example, here in a cut is seen a little piece of blade and the hub, can be just substituted by a refinement area with larger elements that will host the actuator lines, and this means that the mesh for the actuator line case does not need the high power computing, but it can be run on a local machine. So we will focus on the full rotor and resolved geometry. Before to start with the simulation, some scalability test has been done on the medium mesh, and we can see that OpenFOAM in the configuration, directly on the configuration on the domain of the production runs, scales up to 8 ARCHER nodes with a perfect scalability, and therefore, we decided to use a maximum of 8 Archer nodes, so 1024 MPI processes for each simulation. We check also the sensitivity of the solution to the grid and tried to get solution from a coarse, medium, and fine refinement level of the grid. And we can notice that even with the coarse, we are quite close to the experimental measurements, but with the medium level, also the axial force to the rotor is getting closer. Not so much difference, making a grid that is double the medium. So we found the medium level as the best option for the next computations. So some information about the simulation on ARCHER2. The 3 steady simulation with axial wind run for 15,000 pseudo-time steps to arrive to convergence. Pseudo-time steps because for steady simulation, the simple algorithm implemented in OpenFOAM makes a sort of time integration, but with a pseudo-time to arrive to convergence of a steady state solution. This was run on 4 Archer nodes, and each simulation took just 3 hours world clock time, corresponding to around 1.5 thousands of core hours. In the case of time-dependent simulation for the misaligned wind, things are much different. As you can see, just to run 6 seconds of physical time using 1 degree of resolution per time step. So setting a time step that corresponds to the rotor making 1 degree of revolution, and for each time step, 7 iterations of the simple algorithm. And this results in 29 hours, more or less, so 30 hours of clock time for each simulation on twice the nodes, 8 ARCHER2 nodes. And so this is about 30,000 core hours per simulation. Results are quite good in terms of integral loads, and we see an example of integral loads here as the axial force and torque at the rotor. We see in these tables the comparison for all the cases. Remember, the first 3 cases are for 0 misalignment, while the second 3 cases are for 30 degrees of misalignment. That is quite a lot. And we have experimental measurement compared with a full rotor and actuator line simulation. This WIP is work in progress because some of the simulations are still running. But we see that we have quite good agreement almost in all the cases, apart from the cases with high wind speed, which corresponds to the worst case in terms of numeric accuracy, because we have a lot of separation, and branch modeling, but also actuator line modeling are not as accurate to give us better solution for this case. But however, because we are interested most in operational condition for the turbine, we don't expect the turbine to work in stalled condition like this one. So having good results and small errors in case with lower wind, this is the let's say rated operational point, operational point of the machine. And we see quite good agreement for all the simulation we did in this case. Also, validation more locally we can do with pressure measurement over the blade sections. In this case, the pressure was measured around the aerodynamic profile for these three sections that corresponds to these three columns of these plots, while the rows corresponds to the different wind velocity cases. And we see that with the medium grid, this kind of comparison, of course, is only for the resolved geometry, because we need to resolve the shape of the aerodynamic profile. And we see a very good agreement in all the cases for the pressure measurement, another point of validation for this system. Then, having done the validation, we can go to the final case, which is the more expensive and maybe more interesting in this case. So let's put the rotor in a working condition that is a possible wake control setup. And so the rotor will work at 15 meters per second is the rated velocity of the wind respect to this rotor, and we set up at 20 degrees of misalignment. And in this case, because we want to avoid diffusion, or we want to follow the wake with the highest possible resolution of the grid, the grid is the highest refinement level of the grid is extended for few diameters downstream from the rotor, giving us a grid of the order of 113 millions of nodes, or less. The cells are more or less the same, similar number. And we see that because of this refinement, the number of cells is almost 3 times or more respect to the grids that we used for the validation case, but the refinement at the rotor is the same as in that case, so we don't need to repeat the validation. We just extended this refinement region. This is a cut, so this refinement is basically a cone inside the cylindrical domain. And to also try to catch a better accuracy for the wake resolution, we switch in the end of the simulation to an hybrid delayed detached eddy simulation for the turbulence modeling. And what we get is that about the simulation now, we see that for one simulation runs for 6 seconds at 2 degrees of revolution per time step with the same amount of iteration, we get 75 hours of walk clock time. So I think this is more or less 3 times, but it's let's say similar to what we were is in line, I think, with the former measurement of the time of the execution time, because of the difference of the cells in the computational domain. And for the extension of the simulation with the hybrid model, that is about 1.5 seconds of physical time, and with a very small time step of half a degree of revolution per time step, we get almost the same amount of time for running. And this is what we get in the end, a nice shape for the wake. We can see, for example, the wake released by the rotor. Here you see the rotor, and the surfaces that you can see here that describes the so-called tip vortices of the blades are surfaces of isovorticity. Vorticity is mathematical, is given by the cross product between the nabla operator and the velocity. Is a way to measure the vorticity, and so is a way to catch the vertical structures. And we can see also cutting the flow field at 0.5 diameter. So here, 1 diameter and 1.5 and 2 diameters downstream the rotor, how the wakes evolves in the simulation. We must notice that wake get lose the symmetry because of the misaligned configuration, but also in this case of runs refinement grid, we have diffusion of the grid, and this is probably due to the high production of turbulence at the blades. This kind of effect we will see is less pronounced in the actuator line case, because indeed there are no walls and the production of the turbulence in that case is smaller. So let's go on. Some first comparison between the simulation done with the resolved rotor geometry and the actuator line model. We're quite happy to see that the reduced order model gives very similar description of the wake in terms of vortices. What we see here is a cut of the flow field showing the contour of the Q criterion, which is another quantity that is used to visualize, to show vertical structures in the field. And you can see here also that there is the presence of a little deflection of the wake with respect to the main current free stream direction, which is this one, due to the reaction to the thrust force, as expected. And this is even more, is possible to notice it more here on the velocity contour plot. Again, the resolved geometry on the left and the actuator line simulation on the right. And we see that with respect to the main direction of the wind, which is that white line at 20 degrees respect to the axial line, the wake is getting deflection with respect to the main direction. And if you imagine to have another wind turbine on the line just behind the first one at a certain distance, making this one working with the misaligned wind condition can free a part of the rotor of the second turbine that we can imagine to put downstream. So also this deflection seems to be catched by the low order model. We see less diffusion of the wake for the reason I was telling before. Also, the loads that are expected at the rotor from two models are very close. Maybe there is a bit more torque in the case of actuator line model, but the error it's quite small for this kind of simulation, so it's acceptable. Just a few words about what happened when we change the turbulence model in the rotor resolved geometry simulation. On the red lines are the wake contour, the velocity deficit contours for the URANS model using the layered detached eddy simulation. Give us a bit more refinement of the wake. It can extend it for at least one more diameter from the rotor, but still using this kind of mesh is not optimal to get best accuracy of the far wake field, which can be an improvement and maybe a possible extension of this work. Using more suitable, using boundary conditions of the turbulence and the grid that are more suitable for LES type simulation. Of course, that kind of grid will be much larger in number of elements, and that is something that needs to be accounted before start this kind of simulations. Okay, so this was the first part. Let's move to the second part. It will be faster than this, because it's about just one simulation. A little overview of the method. It's a method that we developed in the last years. Basically, we select a site to generate the wind condition. So in that site, in this particular case, we selected the site of installation of a research platform that's called the ARCHER2, and a particular day of measurement for the test and a particular time. And then for this location, we can perform mesoscale simulation with a numerical weather prediction. In this case, we use the WRF, Weather Research and Forecast tool, which is one of the mostly used tool in this kind of analysis. And then starting from this mesoscale data, which are given on a grid that is around 1 kilometer of sides for the cells, in an area that can contain the wind farm, so few kilometers of area, can project and adapt the solution from this numerical weather prediction over a very high, much more refined domain to downscale the prediction given by the forecast tool. And this can be then later used, of course, for the simulation of wind turbines. In this particular case, the local scale simulation that we are interested in to increase the accuracy of the wind prediction is based on run simulation with the K-epsilon turbulence model. We need to add the buoyancy effects and the temperature transport equation to the set of governing equation, plus some forces and sources to account for example, Coriolis force and geostrophic wind drag, or also the thermal production of turbulence. And also in this case, we are interested in see what happens if we add the motion of the sea waves on the sea surface. How to do this? We take the grid. I hope you can see it well, because in my view, this got a bit broken after the. Okay. Should be projected on the ground, this wind rows, but however, the idea is that we have the mesoscale grid that has these large cells, and the local scale grid, which is this refined domain box, in which inside we model the waves imposing a motion of the ground surface with a sine wave of period 8 seconds, length of the wave 35 meters, and the height of the wave is 2 meters. These features of the waves have been obtained from data about the waves on that site that we selected for the test. And the wave is a simple sine wave oriented in the same direction of the wind. For this kind of simulation, we require less resources because the grid is smaller. We will see it's about 12 million of elements, but the simulation is quite long because we need to cover a large domain. In this case, we run 600 seconds, so 10 minutes of physical time at 0.05 seconds for each time step, and the usual 7 pinball iteration for each time step. For this simulation, in 4 ARCHER2 nodes, we need 6 hours of work log time. And also in this case, the grid for the production test was tested respect to a coarser and a finer level of refinement for different grids. And we see that with this amount of cells, we get quite no difference on the root mean square error of the velocity, direction, and turbulent kinetic energy at the measurement point, the test point. So we can get this as independent grid solution mesh. And this is taking the wind vertical profile in the center of the CFD domain that I showed before. The comparison is with the mesoscale model, and after passing to the downscaling episode with the CFD, we see more detailed wind profile, especially on the first part of the boundary layer. And in this case, it's a steady state simulation used to start up the unsteady simulation, and then the blue line is the unsteady simulation with the effect of the waves. And you see also from the plot on the right that the turbulence due to the presence of the waves is increasing in the first 50 meters, more or less. But also with this technique, we can obtain a wind that can vary its direction along the elevation in the domain, which is possible, for example, with the theoretical models and with the standard. Also, the velocity you can see from the plot on the left shows a variation that contains also the thermal convection, and that's why we don't see a profile similar to the one that I showed in the first slide, in which, for example, the theoretical profile of the wind should be given by a logarithmic curve. More in detail, the effect of the waves can be seen from this picture, and the picture on the left shows the production of turbulent kinetic energy in the first 30 to 50 meters above the sea level. And this turbulence production is due to the upwash that you can see in the picture on the right, which shows the vectors of the wind velocity, and the velocity of the waves push include an upwash effect on the first layers of the this effect can be visible, of course, here, where the solution gets a bit slower than the case without the waves, which is the dashed one. Okay. In the end, why we should do all of this work, and this can be seen here. If we see a rotor of 100 meters more or less blade, we see that using a theoretical profile, this orange line is the wind velocity that the rotor will see, and the blue line is the one that we get from the simulation. And you can see that there is a difference in the way that the blade sees the velocity during their revolution, but also in the direction of the wind that is fixed along the elevation for the case of the theoretical profile, but shows a strong variation in the case of realistic wind profile that we can obtain with this kind of methods. Okay, I hope it was not too long or it was enough understandable. Of course, I'm available now for questions or later for curiosity if you have. And thank you for your attention.
Thank you very much for that, Alessio. That was great. Yes, so if anyone does have questions, as I said at the start, feel free to either write them in the chat or to click on the raise hand button.
Okay, I see the question of Mark. Thinking of actually, Mark, I answer your question, and basically the point of having more blades would introduce more sources of disturbance on the wake. Furthermore, it was proven by technological facts that the 3 blades configuration for wind turbine is the optimal. So yeah, more to follow your question, probably using a 2 blades configuration would be better. But still, if you are able to catch energy from the flow with your rotor, this interact with the flow, so the wakes behind still is disturbing for the downstream turbines. That's why these systems are trying to deflect and to drive the wake in another a bit on the side of the rotor. I think Bruno raised the hand, maybe.
Yes, thank you, Dr. Castorrini, for the. Thank you for your presentation. I have a question about the modeling of the wave.
Yes.
That you presented in the second part of your talk. I imagine that the mesh motion adds a lot of computational costs to the simulations, right? So have you considered using another approach like immersed boundary, something like that, to model the waves?
Yeah, actually, the actual practice is to use that, basically to use the volume of fluid approach that include a filter on the density and allows you to simulate also more complicated waves, structure, and etc. In this case, I wanted to keep the highest possible level of accuracy of the boundary layer cells around the wave surface. And when you use the immersed boundary or the volume of fluid case, the cells that you are using, the grid that you are using around the waves cannot be so accurate as a boundary layer mesh that is just moving along with the wave motion. Of course, there are pros and cons for both the techniques. In my case, you need to model every wave motion you want. In this case, was a very simple sine wave. If you want something more difficult, you need to put more harmonics. And also you have just linear waves in this case. In the other case, you can have directly the simulation of the wave motion. But I think for so large, with so large domains, this one was 4 kilometers domain, to get high accuracy with the volume of fluid approach, you need, I think, much more cells.
Thank you. Thank you.
Okay, I see a question from Bonaventura. Motion of the rotor imposed of fluid. The motion of the rotor is imposed in this case. Then I can answer Rodolfo. Presentation. In the presentation, I assumed that was Okay. Yeah, that's a good question. Of course, this value are selected after some tests about the current numbers. The average current number for the simulation with the 2 degrees was around 0.9. So it was quite at the limit, but that was a matter of use of the resources to arrive to a let's say, a convergent solution also with respect to the averages of the flow. 0.5 degree, of course, the current number is 1/4 in that case, the average. A good solution was done for the validation test with 1 degree and 0.5 of average current number. Okay, David. Okay, David. Because I decided to don't simulate the presence of the ground and the tower, I don't need to have different volumes in the domain that rotates at different velocities. So the whole domain is rotating and is rotating with the rotor. So I can decompose just one time at the beginning and then impose the rotation as a rigid rotation to all the domain. However, when you use more, when you use a multiple zones that can have relative velocity one respect to the other, there are techniques that you can use in OpenFOAM, but probably in that case you will not get so good scaling capability on the HPC system. Yeah. Filippo has a question.
Hi, Alessio. Thank you very much for the interesting talk. Just a quick question on the modeling of the rotor. So you showed the difference between the rotor that is fully resolved and the actuator line, so the near wake and the far wake. There seems to be quite a big difference between the two in terms of wake decay, especially for the far region. You mentioned this might be to like diffusion, turbulent dissipation. Do you have any validation maybe for velocity profiles for the streamwise velocity at higher distances?
Yeah.
The rotor
no, the measurements can provide you a description of the wake, just a few diameters in the near wake. So for that, I can make a comparison with the measurement, but for the far wake, I don't have the way to test it. But with that high diffusion that you see, I think for this model, this particular model, there is no sense to make such a comparison.
Okay. Okay. Thank you very much.
I'd just like to say, in case there are any more questions, we can run over the time. We're scheduled for 4 o'clock, but this talk has been recorded, and for anyone who has to leave now, it will be up on the ARCHER2 website shortly.
Okay. I think there is not any more questions. If I miss some, just tell me.
I think you got all the ones in the chat. Does anyone else have any final questions? Okay, in that case, thank you all very much for coming, and thank you, Alessio, for giving that talk. That was excellent, and yes, see you all at the next webinar.
Sure. Thank you all.